aim of this project was to design, build and test a wing for an unmanned aerial vehicle, such as that you'd find in the Air Force. Composites are inherently lightweight materials. The design process for both teams was identical, where we began with a basic back-of-the-envelope calculations, assuming simplified geometry, effectively a box section cantilever beam. In order to reduce the overall cost, the majority of the wing consists of glass fibres as opposed to the more expensive carbon fibres. However, glass fibres alone cannot provide the stiffness required. Therefore, carbon fibres were used in moderation. Both teams ended up designing for two carbon rails, one sitting on the upper surface and one sitting on the lower surface, travelling the full span of the wing. The design process is ultimately iterative, so the geometry was further refined from a simple box section to a more complex geometry that accurately represents the final component. All calculations were carried out using material data from the manufacturer's data sheets. This, however, is not sufficient when designing critical components. Therefore, substantial material testing needed to be carried out to verify and validate the material property data we did have.
There were two main reasons why we conducted material testing. The first was to get hands-on experience with manufacturing and the testing procedures and standards that are used in industry. The second was to confirm the material properties and check that they correlate with those that we were given by the manufacturers. And this will allow us to proceed with the next stage of the design.
Ultimately, the structural response is a combination of both torsion and bending. Finite element analysis was used to validate the analytical results. It was also used to determine any stability issues, such as buckling. All in all, the results from the finite element analysis correlate nicely with those calculated analytically.
Composite manufacturing, there's no hard rules, there's not a single rigid way to make your part. And over the years we have developed a multitude of approaches which differ fundamentally. So you can start with wet fibers or dry fibers, you can add the temperature to the equation, you can apply pressure, both positive and negative, to your choice. As a CDT, we're split into two teams. So one of the team used the wet layup approach. It's an early rudimentary method, but it's been well developed over the years. And this was coupled with vacuum bagging. So the bag was put over the part and the air was sucked out. That ensured better finish and consolidation of the fibers. The other team used the VARTM or VARTM method. This stands for Vacuum Assisted Resin Transfer Molding. It's basically draping your part entirely with dry fibers, then putting a bag over it or a mold, sucking the air out and introducing the resin into it, so the resin fills the void and that creates your part. The methods, there's no right or wrong there. Both methods can be used. It just depends on your criteria you want for your part. The bottom line is make it work.
So the key drivers in this analysis were stiffness and strength, and this test allowed us to determine how accurate our predictions actually were. The models we created were low fidelity, which means they were quite simplistic in nature. With that in mind, we could only really accurately predict displacement more than strength.
The data collection during the testing, we used a combination of strain gauges on the wing, and then for the displacement measurements, we had potentiometers underneath the tip, and then we also extended the end of the wing here with targets to use with the video gauge. We also had a high-speed camera that was focused on this area here because this is where we were expecting the damage to take place. We used two rosettes on either side on the rails, and then linear gauges on the trailing edge, top and bottom also. The load was applied using a hydraulic ram that was positioned above the wing and attached through the extension of the rib at the end here. These different techniques are not necessarily straightforward, so it's been good for us to have experience of how to set those up and use them and analyse the data.
The testing revealed that our structure was actually stronger than we had predicted it to be, and that deflections were much higher than we initially predicted. The wing itself could have been stiff enough, but we are measuring, in addition to the stiffness of the wing, the deflection of these parts over here, which we did not account for in the design. The wing failed at the bolted joint, which we expected, as it is the weakest part of the structure. There was a local compressive failure at the top face, where the composite both fails compression and delaminates. Of the two manufacturing methods, RTM matched our predictions closer than the hand layup did. That was because we had better control over the final shape of the component, and the quality was improved.
The project as a whole was a very positive experience. We've gained a wide set of skills and drastically increased our experience, especially the hands-on manufacturing aspects of it, and it sets us up in a really positive way for our PhD.